Alright, let's practice drawing and analyzing a parallel circuit. So in this one we have three resistors connected in parallel. Connected in parallel means there are three resistors, therefore three pathways through this circuit. So we have this massive 90 volt battery. And I'm going to draw, here's my first, well let's just make that a wire. First resistor, second resistor, and third resistor. Connect all those up. And don't forget to label. We'll make this R1, R2, and R3, and the resistances are 20 ohms, 30 ohms, and 60 ohms respectively. We're going to use this VIR chart just like we did with series circuits. It'll really help you out. And just like with series circuits, there are some things that we can put in here that we know automatically right now without doing any math. First of all, the resistances, just like in series, we know those, 20, 30, and 60. Again, realize that if you go to another class, things might not be this easy. You might have to modify your chart based on the fact that there might be more than one resistor on a branch, but that's something we can talk about another time. The total voltage also we know, that's the voltage of the battery or the voltage source, that's 90 volts. Now in this class only, since there is only one resistor on each branch, actually there's something else we know in parallel that we didn't know in series, and that is, if you look back on the characteristics said that voltage drop across each branch is the same. Well, since each branch only has one resistor, we can go ahead and assume that this voltage drop is 90 volts all the way up. Each one has its own direct connection to the battery, so you're going to have a 90 volt voltage drop across each one of those resistors. So that makes parallel kind of cool because we know more than half of it right now without doing any math. However, the math that we do is a little bit more complicated when it comes to calculating total resistance. We can't just add them up this time. We have to add reciprocally. So remember, this is where we do the 1 over everything. So 1 over the total resistance here equals 1 over 20 plus 1 over 30 plus 1 over 60. Alright, you could do common denominator stuff and make it all complicated, but this is 2015 and we have calculators, so I recommend just put those babies in parentheses and just put it directly into your calculator. Right? So in other words, what I did, it looks like this: 1 over 20 plus 1 over 30 plus 1 over 60 is 0.1, right? So we get 0.1 from this, but I want you to put a star right here because this is the most common mistake people make. So many people want to take this 0.1 and put it in here as the total resistance, and that's not the case. Remember, this is equal to 1 over RT. So to get the total resistance, we have to do 1 divided by whatever it is we got there. 1 divided by 0.1. Now be careful, don't make the mistake of doing this divided by 1, because anything divided by 1 is the same thing as itself, so it's not going to change anything. If you do this, 1 divided by 0.1 gives you 10. 10 ohms is the total resistance, or the equivalent resistance of the circuit. And now it's easy because all we don't know is the current in each one. And as you know, if we have 2 of the 3, we can get the third one using Ohm's law. For current, it's V over R. So total current, voltage divided by resistance, that's 90 divided by 10. Do not use your calculator for that one. If you can't tell me that's 9 amps, you got a lot of problems. And at this point, resist the urge to fill in the rest of the currents. We did that in series. That's not true in parallel. We have to calculate it separately in each branch, because remember, each one of these is going to have a different current because they each have a different resistance. The current now has choices, quote unquote choices. So we're going to have more current running through the smallest resistances, less current running through the largest resistances. So we're still going to use the same equation to calculate current. For resistor 1, voltage divided by 20, 90 over 20. For number 2, it's 90 over 30. And for number 3, 90 over 60. Right? Hopefully you can look and see right now, as I already explained, but before we even do the math, we expect to get the highest current from the lowest resistance, lowest current from the highest resistance. If you do each one of these, I think this was 4.5, 3, and 1.5. Am I right? Yeah. And it's a good thing we get those numbers because, well, I'll show you in just a second. 4.5, 3, and 1.5 add up to 9 amps. So in series at this point we did a check to make sure everything was okay. We can do the same thing in parallel. In this class, the voltage column should look all the same. In this class, the current column should add to the total, add to I sub t, total current. And there's not a specific mathematical check for the resistance column, but you do need to realize that the total resistance is going to be less than any of the individual resistances. If your total resistance is greater than or equal to any of the others, you did something wrong. Now, realize at this point that it's possible to get a resistance that's less than any of these and still have it be wrong. That is, if you did this, right? If you take the 0.1 and put it in here, obviously it's still less than the rest of them, but that's not correct either. So for this one, I'm going to say RT is less than R1, 2, that's a 2, or 3. All right. So take a minute and do this circuit. Pause the video real quick and see if you can run through this. I'll put the answers up in just a minute to see if you got it right. Alright, here's what you should have gotten for that parallel circuit. Look it over carefully, make sure your work matches mine, make sure you've got all these numbers here. If you didn't get something right, try to go back to your parallel characteristics or to this previous circuit up here and see if you can figure out what you did wrong on there. If you can't figure it out, come and ask me in class.